Let's take a look at another example of sinusoidal steady-state analysis techniques. In this example, we're asked to find the power dissipated across the 10 ohm resistor. So we'll look for P10. What is that equal to? We can use our power equations, current times voltage, our current squared times the resistance, our voltage squared divided by the resistance, where we're careful to label in time domain where is that I10, where is that V10, giving the appropriate subscripts. So we need to pick a strategy. We can solve for power using any of these equations. If we choose to solve for the power by finding the current through the resistor, then our P is equal to, our power is I10 squared times R. We can choose a strategy to solve for it in frequency domain and solve for our I10 phasor, and our I10 phasor, which has the magnitude and phasor angle. We can then, once we solve for that phasor, convert it back to time domain using the magnitude of the phasor as the amplitude of our cosine, and we have a phase shift of the angle found in our phasor. But what we need here is the frequency. So we'd have to find the frequency. Based on the frequencies, we can find our impedance. So what is the frequency associated with this circuit? We have two current sources. If we look at each of these current sources, they both have different radian frequencies. Since they don't, if we used a radian frequency of 5 radian per second, the impedance associated with this 0.5 farad capacitor is different than that associated with the impedance due to the 3 radian per second current source. So we have to use superposition to solve for this circuit. Again, at 3 radians per second, the impedance of our 0.5 farad capacitor is negative J over omega C, or negative J 2/3, which is approximately, we can put that approximately to 4 significant digits. Whereas at 5 radians per second, we're using negative J divided by 5 times the 0.5 farads, and we get negative J 0.4. So at 5 radians per second, the reactance of this 0.5 farad capacitor is negative 0.4 ohms. At 3 radians per second, the reactance due to this 0.5 farad capacitor is negative 2/3 ohms. Similarly, we see the difference in the 0.2 farad capacitor. So again, we must use then superposition. The phasors are not affected by if we look at this phasor, this is just going to be our 5 angle 0 degrees. This will just be equal to 2 angle 0 degrees. So the phasors aren't affected by the frequency. They are when we convert back to time domain. So let's look at this circuit. We'll have to use superposition. We solve for the impedances. We'll look at this circuit that kills the 2 amp source. We'll look at this circuit that kills the 5 amp source, and based on just these sources, we'll find an I10 prime phasor, an I10 prime phasor. We'll convert each phasor back to time domain, and then we have to sum the two currents, time domain currents together, and it's those summed currents that we will square to find our power in time domain. This is important. For one, power is not linear. We have to find the two currents separately, or find one current and then square the current. We cannot say that, we can't at this point say that, you know, our P10 prime is not equal to I10 prime squared times 10, and our P10 prime is not equal to I10 prime squared R, and our P10 is not equal to P10 prime plus P10 prime. We can't do that. Why can't we do that? Because power is not linear. But we can sum up the currents, square the final current, and multiply that by 10 ohms. So there's our strategy. Then we can go through and we can find our I10 prime. I10 prime is easy enough to find using a current division. So we have our current division. Since we only have 2 branches, it's easy enough to just use the impedance. We realize with current division the admittance is a little bit easier, but we'll just use the the impedance of the opposite branch divided by the sum of the branches, and we can then find our I-10 phasor using current division. We can find our I-10-10 phasor also using current division. This 2 amp source is flowing downward, so it's going to be flowing upwards. We just use through each of these branches, and the sum of these then 2 currents will be our final. So that gives us then our I-10. We'll do that in red to be consistent. Our I-10 prime is equal to 811.7 cosine of, since this was originally, this was our omega is equal to 3, we drop that radians per second, and over here we have our omega is equal to 5 radians per second. Whenever we're working in frequency domain, we have to make a note of the frequency. So this is our 3 t minus 76.86 degrees, and our I-10 prime is equal to 7. And this is, of course, milliamps. Sorry, let's go back. We might make sure we note our unit, milliamp, 79.23. And we'll go back to blue. Cosine of 5t minus 82.03 degrees milliamp. Now we have the 2 currents, and we can say that our P10 is equal to 10, our R, times I-10 prime squared. Well, actually it's I-10 prime plus I-10 prime. The entire thing is squared. So it's our 10 times 811.7 cosine 3t minus 76.86 degrees. That's in parentheses, plus 79.23 cosine 5t minus 82.03 degrees. All of that's squared, but since this is a milliamp and this is a milliamp, our answer will be in micro watts, because we're squaring 10 to the negative 3 times 10 to the negative 3. Okay, that's it for power. We will look at power specially in Chapter 11. So this is a good lead up to our time domain power consideration for power in AC circuits. That's it for this video.